Hello everyone and welcome back to the class of fundamentals of particle and fluid solid processing. So, we have covered a lot of content in this course, and now finally we will be talking about the colloids and the nanoparticles, a special section of these particles. Now these are of huge importance nowadays because they are the cornerstone of some cutting edge research that is currently going on. And also this concept or the details on these nanoparticles will help us to understand a certain extent of the phenomena that we have considered in the previous sections. For examples, why the particles are cohesive in nature, the fine particles are cohesive in nature typically or difficult to flow, and what can be done to separate them. So, if we go into the details of these fundamentals of colloids and nanoparticles, then this will shed some light on the mechanisms or the fundamentals of fine particles that eventually we have handled. Now, colloids are typically a very fine particles that are suspended in a fluid and have one or more linear dimensions of around 1 nanometer to 10 micron or even lesser than that. So, we can understand the magnitude of the length or the linear dimension we are talking about. Now, we have come down to the nanometer range. Now, these fine particles we will interchangeably using here as the fine particles, and when these are suspended in liquid are the colloids. Now, in this case what becomes a critical factor is the surface forces, because these small particles, if we look at their mass, these are of very small amount of mass. Now, these surface forces, that is the reason of being fine particles as cohesive in nature. It can exhibit the behavior of high viscosity of concentrated suspension, and it also results in very slow sedimentation, and that is why we spoke about sedimentation in some external field like the centrifugal field and etc., because by gravity separations this kind of fine particles cannot be separated. These remain suspended for a longer time. Now, the reason the surface forces are important, because it provides, these fine particles provides a very large ratio of surface to mass. Now, the mass and the volume is related with the density. Now, for a fixed density of the particle or the bulk density, the material density of the particle, so this surface area and the volume ratio, considering a spherical particle, say it is 6 by x. So, if the particle size, which is the x, the diameter of the particle, it goes down or decreases, we can see that the surface area per unit volume increases. Now, these actually have a lot of implications in several research areas like the nanotechnology, microfluidics, and all these cutting edge research areas. So, also it finds widespread applications, these fine or the nanoparticles or the colloids, in paints, ceramics, food, mineral, paper, biotechnological industries. Now, the reason we are talking about this surface force is that this has a very small amount of mass. For example, this 10 nanometer of silica particle has a weight or a mass of in the order of 10 to the power minus 21 kg. So, that means the body force on these small particles are virtually insignificant, because the body force results from the Newton's law of motion. Okay. So, this relative dominance of the surface force on the smaller particles is actually makes it difficult to understand, because the surface forces are not only it comes from several electromagnetic forces. It depends on the surface property, material property, the intervening fluid property, etc. Whereas the body force is relatively easier to understand, and that is why we will see in this section in a bit details that what are the surface force that actually dictates this behavior of the fine particles of the colloids. Now, as I am repeatedly mentioning, this magnitude of body force is much lesser than the surface force, and that dictates the behavior of this nanopowders or the colloid suspensions. Now, these surface forces are the physicochemical interactions between two molecules or two atoms, and the examples of these surface forces are the van der Waals forces, electrical double layer, bridging and steric forces, etc. These forces can be attractive, and the summation of these forces can be attractive or repulsive, and that actually dictates that whether the particles, the two different particles will be coming together, or it will be repulsive in nature, so that they will be kept away at a certain distance. Now, this thing, as I mentioned, depends on the material property, fluid property, and the other most important is the interparticle distance, the distance between the two particles. So, we can easily remember the Coulomb interaction, the Coulomb chart, the Coulomb's law for the two such charged material. Now, we will be coming into that. Okay. Now, before that, this another feature or another effect of this very small amount of mass of these fine particles or the nanoparticles that has implication is that the Brownian motion of those particles, because these now are so fine or so small and very minuscule in mass that it behaves as if somewhat like molecules, and they easily diffuse into the liquid. So, there are random motions of these particles which we typically know as the Brownian motion. Now, in Brownian motion, this in 1827 was observed by Robert Brown, after whom this name has been mentioned is the Brownian motion, is that the motion of, he observed the motion of pollen grains in water, and these are this such kind of random walk has been named after that. So, what happens is that the neighbor thermal energy or the surrounding thermal energy, okay, is basically translated to the molecules of the liquid that causes its molecular vibration. Now, as the molecular vibration happens, it collides with each other of those liquid molecules and also with the surfaces of the suspended particles, suspended fine particles. So, this collision results into this random motion of these particles, and a simple, let us say, the kinetic model can help us that what would be the average velocity of these particles. So, if we assume that the all thermal thermal energy is being converted to this molecular vibration, so neglecting all other forces or ignoring drag forces, collisions and other factors, we can equate the average thermal energy, which is 3/2 kT, where K is the Boltzmann constant and T is the temperature in Kelvin, that with the kinetic energy of the particle with the average velocity. By equating these two expressions or these two terms, this can give us this average velocity of the particle. Now, this expression, from this expression we can understand that with changing temperature this velocity will be influenced, or if we increase the temperature the velocity will increase, the Brownian motion will be more rapid or random. If we decrease the mass of the particle, the velocity will be higher. So, this expression tells this simple thing, and it is useful to understand this phenomena, that as the particles becoming smaller and smaller, the mass goes down, and as the mass goes down, it has a higher average velocity during this Brownian motion. Now, such simple analysis cannot be used to estimate the actual distance travelled by the particle, because the actual distance travelled, say this between these two particles, is L. But it does not just come across that length, it goes through like this zigzag path, this random path. This is a random structure, random path. It can follow any random path. So, the actual distance that it travels cannot be calculated by this velocity. So, now if a solution, say, or a suspension is stable, then in thermodynamics by principle it has to be in its lowest free energy state of a suspension, and that means the particles will be uniformly distributed throughout the suspension. So, this Brownian motion basically a mechanism by which this resulting random walk generates a uniform profile inside the or in the suspension, so that the particles can organize themselves throughout the fluid volume in order to be in the lowest free energy state. So, as a consequence, diffusion of particle happens from high to low concentration region. Now, in order to estimate the length it travels, Einstein proposed a one-dimensional random walk model, which says that this length that it travels is the square root of 2 alpha t, where alpha is the diffusion coefficient of the particles. He further developed a relation between the hydrodynamic drag or the hydrodynamic frictional drag with this alpha, which is the diffusion coefficient, and that is proposed in this manner, that alpha f, where f is the hydrodynamic frictional coefficient, which is Fd by u, is equals to Boltzmann constant multiplied by the temperature in Kelvin. Now, this u in this expression is the relative velocity between the particle and the fluid. So, it provides us, this expression provides us an estimate that how much length these particles will travel. Now, with this, say in the creeping flow, we know this f value from the Stokes law, or the expression of f from Stokes law, which is 3 pi x mu, where x is the diameter of the particle, mu is the viscosity of the suspension, which means we have alpha is equals to kT divided by 3 pi x mu, which implies that the length L that it travels is of this expression. This expression shows that this length it travels is dependent on the temperature, particle size and fluid viscosity. It also shows that this time and the length it travels is related with the root square relation, square root relation. This length or the average length is also called the root mean square distance. It is indeed one dimensional motion, but in reality this is the 3-dimension motion of the particles. But the reason this expression is important or has implication is that in sedimentation, say, that is our concern, because we want to separate, say, the solid particles, or our main objective is on the solid particles or the fine particles. So, during sedimentation, the motion of this particle is considered as one dimensional, that is in the direction of the gravity. And but in that time, during that period, it is not in the other two orthogonal directions. So, that is basically the reason that this expression has importance. But in 3D, analogous relation can be developed, and that has this L is equals to square root of 6 alpha t, this relation. So, that means we have understood that why this Brownian motion happens, how to estimate the length, how much it travels a certain particle in one dimensional random walk model, and what are the dependent parameters, that which parameters influences this length that it travels or its average velocity. Now, the surface forces that occur, these surface forces are basically resulting from summation of intermolecular interaction forces across the intervening medium. Now, these intermolecular forces comes from the electromagnetic interactions between the atoms. So, generally a force between two particles is dependent on the surface to surface separation distance and the potential energy at that separation distance, and the relation between these three is this expression, that the force is equals to minus dV by dt, the potential energy, and this d stands for the separation distance. Now, these particles or in suspension, it always try to attain the lowest energy configuration by thermodynamics. So, the particle separation distance would be, when there is nothing to do with any other external forces, it will try to achieve the lowest energy configuration state. Now, that means there is a equilibrium distance between the two particles, and when we try to make them very closer, there is a strong repulsive force at 0 separation distance. That means when they are in contact, okay, then they have, or if we try to penetrate, say, one surface with the another, there is a strong repulsive force at that distance, and that is the reason that in one certain space there can be just only one molecule. So, the force profile and the energy profile typically looks like this kind of profiles. Now, typically what happens now, this first one is the energy versus the separation distance, interaction energy versus the separation distance, and this one the corresponding force and the separation distance. So, usually the convention is that when this energy or the force is in the negative, it is the attractive force, and when it is in the positive values, it is the repulsive one. So, this happens when the interaction is there, and this happens when the repulsion is there. So, here we can see that there is no force at equilibrium separation distance, which is at the minimum energy state. Now, so which means now if we try to make them further closer, there is a huge repulsive force that acts in between the two particles, and when they are separated at a longer or a larger distance, there is a very weak attraction there, and if we try to make them closer or even try to take them apart, then we require a greater force than the maximum to pull them apart. We require a force higher than this to separate them to a greater distance. Now, in case when there is repulsion, the interaction is repulsive, they cannot come in contact because of this potential energy barrier, which is greater than the available thermal or the kinetic energy of the surrounding. So, it requires a greater force to overcome this in order to make them in contact. So, the particles, when they are attractive in nature, they stay in this energy well, minimum energy well. If we try to separate them, we require a higher force than this one, than a maximum one, to pull them apart. The particles interaction, the particle interactions are repulsive in nature. We try to contact them, then what happens? We require to overcome a certain potential barrier, or we require a greater force than the maximum to keep them in contact. Now, the one of the major surface forces that we introduced earlier, or we have seen this earlier, is the van der Waals forces. We have discussed this, but for the sake of coherency, let's again see this part, but in a bit detailed. So, these van der Waals forces are the group of electrodynamic interactions which occur between the atoms in two different particles. Now, it consists of several surface forces like, or the electromagnetic forces or the electrodynamic forces like Kisham, Debye, London dispersion forces, and the dominant contribution of London dispersion force that results from the Coulomb interaction between fluctuating instantaneous dipole moments within the apple. So, London dispersion is basically the dominant contributor to these van der Waals forces. Now, this Coulomb interaction between fluctuating instantaneous dipole moments within the atoms, how it happens? So, let us consider a scenario that we have a molecule. Now, there is a very short distance between the nucleus and the electrons of any atoms. Now, in that case, see that nucleus okay, that is say positive charged, around which the electrons are orbiting, are revolving. Now this electron or the electron clouds, as it rotates around this nucleus, it creates a electron density across or around this nucleus. Now what happens in that case, this, in order to be in a minimum energy state, this say one particle or the one atom would be in such configuration, where this plus sign designates the nucleus of the atom and negative sign is the center of this electron density. So now, since this electron density is shifting with time at any instant in time continuously, okay, this would try to adjust its lowest configuration mode, lowest energy state mode. Similarly, this will happen, or this actually is called the dipole moment. Now these dipole moments will occur in all the elements of this particle. Now these will try to accommodate themselves or rearrange themselves in order to be in sync. Now if the two atoms or say the particles are positively charged, or say the same charge of the same material rather, now if those two are same material, then what will happen, this kind of configuration would result in order to maintain its electroneutrality. So this would be the lowest free energy configuration, and this combined interaction between all the particles in the two all the dipoles in the two particles will create a attraction, overall attraction. So this van der Waals interaction can be attractive or repulsive in nature depending on the dielectric properties of the particle and the intervening media. When there is this, usually the people understand that van der Waals interaction is attractive in nature, but in certain cases, in rare case in fact, this can be repulsive in nature as well. But its strength or the magnitude depends on the dielectric property of the particle and the intervening medium. So if we just summarize what we have seen, is that we have seen the Brownian motion of the particle, the surface force, its nature between the two particles, and one of the major surface forces is the van der Waals force, why it occurs, the mechanism of dipole moment and its attraction. That is what we have discussed today. We will go into this in further details in the coming classes. Till then, thank you for your attention.